Yeah, thank you for the introduction and to all the organizers for the invitation. Well, today I would like to talk to you about semi-invariants in representation theory and some nice subcategories of the category of both modules and two-term complexes of projective modules that arise from the study of semi-invariants. So if when hearing semi-invariants, semi-stability comes to mind, it's because they are closely related to each other. So let me say just a few words about semi-stability. So what's the goal of semi-stability in representation theory? Well, the goal is to construct some geometric spaces that parameterize isoclasses of representations. As Claire said, the problem of enumerating in decomposable and representations of two isomorphisms in general is very hard. So why not maybe study the shape of a geometric space instead? So let me be a little more clear about that. In this talk, lambda will be a finite-dimensional C algebra. C because we're going to do geometry. D will always be a dimension vector over this algebra. And we can parameterize all representations of dimension vector D with an algebraic variety that I would denote rep lambda D. And over this variety, I have an action of a linear group. I will not go into details about that, whose orbits correspond to isoclasses of D-dimensional representations. So why not just take the space of orbits of this action and study it? Well, this is not an easy problem, actually. In algebraic geometry, this is a very hard problem. So geometrists came up with a tool called geometric invariant theory that tells us when we can do this. So we cannot always take all the orbits, but sometimes we take some of them. So we have to restrict to a subset of a choice of good orbits, of good points. And in representation theory, this choice will be given by a parameter that I call theta, which would be nothing but an integer vector, also called as stability conditions. So who are going to be these points? Well, I'm going to say that M D-dimensional representation is theta semi-stable for my given choice. If I can find a function that is almost invariant by the action of the group that I mentioned before. And what I mean by almost, well, it be invariant by the action of the group up to a constant that will depend on the parameter theta that I chose. So if I can find such a function that does not vanish when I apply it to M, then I say that my module is theta semi-stable. And these functions I call theta semi-invariants. Again, not an easy trick to construct them, but in representation theory, we can, thanks to many authors in different generalities. Dirks and Wymans, Coffin and Van der Beek, and Domokos, that say that when you have your dimension vector and your parameter, and you ask them to be orthogonal to each other, then all theta semi-invariants over a variety of d-dimensional representations will be generated by a certain class of semi-invariants called determinantal. Who will be? How do we construct these determinantal semi-invariants? Well, thanks to two-term complexes of projective modules, or as I like to call them, and from now on it will be called a projective presentation. So we take a projective presentation that is nothing but a morphisms between two projective modules, such that is G vector, which is nothing but this difference of dimensions, equals to the parameter theta that I choose. Then I will construct a regular function over the variety of d-dimensional representations given by this association. To every M, I will associate the determinant of a linear space, of a C-linear map between these two C-linear spaces of homomorphism. Turns out this thing is well defined because of the orthogonality condition that I asked. And if you take all of this for all projective presentations, and you take the algebra generated by them, you get all the theta semi-invariants, which is very cool. So the definition that we saw before of a theta semi-stable representation can be rewritten in the following way. What you're going to ask is going to be, first thing, you need your dimension vector and your parameter to be orthogonal to each other. And secondly, you have to be able to find a projective presentation whose G vector is a positive multiple of your parameters such that its associated determinantal semi-invariant does not vanish when you evaluate it over M. And if you're familiar with the theory of semi-stability, you might be telling yourself, well, this is not the very nice numerical notion that I know. No, but it actually is the same. So the second, this is my eraser. So the second property actually implies that for any submodule of M, the pairing between the dimension vector of the submodule and your parameter will always be less or equal to 0, which recovers King's numerical criteria for semi-stability. Another remark that I want to make is that the fact that this quantity is non-zero is independent of the choice of P in the space of complexes up to homotopy. That said, if I take another representative of P in the iso class of P inside of this category, this thing has to be still be different than zero. And what is the category that I will associate to this semi-invariant? Well, this is also a proposition by King. The full subcategory of all theta semistable modules is Y. That is closed under extensions, kernels, co-kernels, and direct summas. That is an abelian subcategory of the category of modules. So this is half of the talk. So what I want to remember is that projective presentations and their G vectors control semistability in the category of modules. So could I do this the other way around? This is the question that I've been asking myself in the last couple of months. And why would someone expect something like that to be true? Well, let me remind you another closely related thing with semistability, that is tau tilting theory. So we have this famous result stating that support tau tilting modules, functorial finite torsion classes, and left-wide subcategories are in bijection all with each other, which are three very important things in tau tilting theory. And it turns out that this class of wide subcategories can all be realized as semistable subcategories of the category of modules. Okay, so this all happens in the category of modules, but it turns out that if I restrict, now I think of the category of projective presentations up to homotopy, or two-third complexes of projective modules, these classes of objects have corresponding objects in this category. For instance, for torsion classes, we have cotorsion, for torsion pairs, we have cotorsion pairs, and for support tau tilting objects, I have tilting objects. So if I wanted to like fill out this diagram and find natural maps between these objects such that everything commutes, you might suspect that the thing that I will plug in here will be related to semistability in some way. So let's do this. A clue towards this result was given by Gusa, Ortodor, and Wyman. They said that if now, well, you take your dimension vector and theta as before, that are orthogonal to each other. And now if you think about this function, so in these functions, we fix the p's and we let m vary. Now fix the m and let the p vary over this variety. Then this function, determinantal semi-invariant, but now with m fixed, will also be a semi-invariant for a certain action over this variety. As we said before, these things respect quasi-isomorphisms, and another thing proved by this author, stated in very rough terms, is that when the quiver is acyclic with no relations, all semi-invariants that respect quasi-isomorphisms of projective presentations are generated by the determinantal semi-invariants given by the modules. So, so this tells us that maybe there is a notion of semistability. Maybe it is numerical as King's stability. And we have a proposition that says that if you take a P and a D and P a projective presentation that is D semistable, that is, you can find a semi-invariant that is not vanishing over P, then the D and the G vector of P will be orthogonal. And for all, well, let me say in rough terms again, sub-objects of P in the category of projective presentations, then I will also have this numerical condition. I cannot go into details, but these sub-objects in this context are called inflations. Okay, is this enough? Do I get what I want? Well, the answer is sadly no, because this actually do not tell me, we had like a necessary condition, but it's not sufficient. Like if I have this numerical condition, I cannot guarantee that there is a semi-invariant that is not vanishing over my projective presentation, and we have some counterexamples. And moreover, most important for me, the full subcategory of this semistable numerical, that satisfies the numerical condition that I saw before, is not even closed under extensions. So this will not give me a nice subcategory that I could plug in the diagram that I showed you before. So let's just restrict then to the following notion. I will say that a projective presentation is M semistable if I can find a semi-invariant such that my projective presentation does not vanish over here. And the proposition is that the subcategory of all M semistable projective representation is closed under all the cool operations in the category of projective presentations. That is extensions, co-cones, cones, and direct summas. These categories are called thick, and no, by no means is my invention. This already existed, for instance, in this context, and introduced by Nakaoka, Ogawa, and Sakai. And the theorem that I would like to finish is that yes, if I consider thick subcategories plus a technical condition that I don't have the time to get into, you can fill out the diagram in a natural way, you can find maps from these objects to my new set of objects, so that everything is commutative and all the maps are bijective. And that's all I wanted to say.